Good morning. I am about to do the solutions for the 9.3 check your understanding just to narrate that and explain, help support those of y'all who might want to check your answers and or need a little bit of extra help. So, about to turn my video off and let's get to work. So, as a quick reminder, it doesn't matter what type of inference procedure you're looking at. If we're talking about an inference procedure, we have got to do our 4C method for inference. We got to choose, we've got to check our conditions, we've got to calculate, and we have to conclude. So we're going to work through all that here. So CNN once claimed that half of teenagers are addicted to their phones. A random sample of 180 teenagers was selected, and 72 reported that they were addicted to their phones. Is there convincing statistical evidence that the proportion of all teenagers who are addicted to their phone differs from zero point 0.5? And so right away differs from, remember, that's a huge indication, like we're collecting evidence for that. So the alternative is P does not equal 0.5. One thing I'll point out is about this study design, this is self-reported. I don't believe this study design very much. I need someone else to check addiction. But based on the data here, and that's what the AP exam would want, let's choose our procedure. Notice I'm not being asked to give an estimate for the true proportion of all teenagers who are addicted to their phones. I am just asked, is there statistical evidence? When I see, is there statistical evidence, that immediately makes me think, hey, this is going to be a hypothesis test or a significance test. And so this is going to be a one sample Z test for proportions or for a proportion. You can also call it a one prop Z test. One sample Z test or significance test for a proportion. Anytime you choose, you also need to identify your significance level. We're going to use an alpha of 0.05. We need to identify what our hypotheses are. And remember, your hypotheses always are going to use the same value given. So the claim originally was that P is 0.5. My alternative that I'm checking is P is not equal to or differs from 0.5. And once you do all that, you should look back and go, you know what? I don't have a definition for what P is. So define P, the true proportion of all teenagers who are addicted to their phones. Notice I'm just going back to the context. The true proportion of all teenagers who are addicted to their phones. If I were you at this point, I would go back up and I would check the 4C method seen earlier, make sure I didn't miss anything. I think that's it though. I've got a procedure, I've got a parameter, I've got my hypotheses, I got my statistic. Ooh, I don't have my statistics, so yes, I need that. In this case, which I usually don't bring this up till later, P hat equals 72 out of 180, 36 out of 90. Sorry, I'm just doing this quickly without a calculator. Divide those both by 18. I think that gives me 2/5. Yeah, that sounds right. I'll figure out later. All right, so there's my choose. Now moving on to my check. Checking, we always need to check for normality, randomness, and 10%. So random sample stated. Check. Um, I can assume that 180 teenagers is less than 10% of all teens. Check. And you can write 10% condition there if you want. Do notice we always want to keep in mind why these things exist, but you don't have to say it every time, at least as far as I'm aware. I'll check on that. But random samples so that we can make an inference about the population, 10% conditions so we can use the standard deviation formula for the sampling distribution. And finally, We have the large counts. Remember, we're dealing with proportions. I need approximate normality, so large counts. And so the original large counts condition is that n times p is greater than or equal to 10. And with confidence intervals, we didn't have a p. Remember here with our hypotheses, we do have a p. So 180 times 0.5, you use the p, is equal to 90 greater than or equal to 10. And n times 1 minus p would equal 90, which is greater than or equal to 10. Notice I substituted in one time. You can substitute values in again, but that's all you really have to do there. All right, so check, calculate. So when calculating, start with your general formula. So general, if I look at that formula sheet, I still have it pulled up. I don't, let's see here. So remember, we're in inferential statistics. We're literally at a stat test. And so remember, there you go, stat test, standardized test statistic. Test statistic equals statistic minus parameter divided by standard error. You don't have to write all that out, but it can help if you're struggling. Keep going back to that formula sheet, right? We're using a z-score. My statistic was that 2/5 or 0 point, well, oops, I'm not substituting values in. My statistic was a p hat. That's estimating my parameter of p. So remember, going back to the formula sheet, I hope that I am, make sure I'm sharing. Ooh, y'all did not see that earlier, so sorry about that. But I went to this formula sheet online and notice I am dealing with proportions here at the top. And so for one population, p hat's my statistic. The mean of the p hat is p. So I'm just pulling my stuff off of there. And because I have p, I can use sigma sub p hat and not the actual standard error. So going back to here, hey, I now have this formula. And now I substitute my values in. Z equals 0.4 minus 0.5 divided by the square root of 0.5 times 1 minus 0.5 divided by a sample size of 180. Now, don't forget, at this point, I'm never, ever, ever doing that work by hand because there's just too many options for an error. Good morning, thank you. Sorry, I should have had this calculator pulled up already. Miss Kowalski, I'll be done with this. I'm just doing the check your understanding for stats. All right, finally. So menu, statistics. Remember, we are running a stat test. That's why you want to identify this early on. It's a one proportion z-test. Null hypothesis was 0.5. Successes was 72, I think, and 180. And we do want a not equal to. Yep, so p has 0.4. There's my z-score. And so z is equal to negative 2.68. Remember, with standardized test scores, you typically want to go to 2 decimal places. Probabilities, you can go less. Now, always draw your normal curve. And because it was a not equal to, we weren't sure what it would actually be. Negative 1. All right, so there's my negative 2.6. And so I also have to mark positive 2.6. So that's the not equal to. I do the positive and the negative. And so the probability that, so we do 2 times the probability that z is less than negative 2.68. Got to double that area. The nice thing is the calculator has already doubled it for us. I don't have to do the work. That's why I did not equal to. So 0.073, 0.073. And so I'm going to go into this on the conclusion in a second, but remember, that's the probability that we get that test statistic or more extreme by chance alone, assuming the null hypothesis was true. So that's pretty unlikely. And so conclude, we're going to first interpret. So assuming the true proportion of teens addicted to their phones is P equals 0.5. Notice I've already got context, so I'm good. I don't have to readdress context every time. The probability of getting P hat equal to less than or equal to negative, nope, not negative. What is that? 0.4 or equivalent on the other side is 0.0073. We reject the null hypothesis that P equals 0.5 since we have convincing evidence. Remember, that's where you need to compare P to alpha. The P value equals 0.0073 is less than my alpha equal to 0.05. We have convincing evidence for the alternative hypothesis, which you really should probably write that out. Alternative hypothesis that P does not equal 0.5. Man, I forgot what the alternative was for a second. All right, in a second, I'm going to show you what the mathematics said, see if they have any differences there. But I don't have a ton of room. I should create another page, but time. 95% confidence interval for the proportion of all teenagers who are addicted to their phones is 0.328, 0.472. One thing I will point out is a confidence interval actually perfectly corresponds to a not equal to alternative hypothesis, because if you're thinking about a normal curve or a confidence interval, it's talking about the middle percent, right? Which is the opposite or the inverse, really, of the two-tailed test, right? We're not having those tails. All that to say, though, with 95% confidence, the true proportion, and I'm leaving out context because of, again, room and time, is captured by the interval 0.328 to 0.472. This does not capture 0.5. So there is, I guess I should have moved that. I would have had more room. So there is convincing evidence P equaling 0.5 is not plausible. Remember that interval is giving us plausible values. 0.5 is still possible, but it's not plausible. All right, hope that was helpful for those who needed that extra support. And that wraps up this narration of the check your understanding.